So, thank you for being here. It's a pleasure to have this chance to talk here in Geneva at CERN. I'm not really used to the CERN-type lectures, so please interrupt me if you have questions. I would like this to be an interactive course, and it's useful for me to get some feedbacks. So actually this is the official title. You have also a list of names of the people working with me at Geneva University. I hope I forgot nobody, since most of them are in the audience, so they can check and tell me. The outline of the talk is probably best seen on this transparency here, where I think it's very nice to see that really this main topic, quantum non-locality, is really central from many different points of view. And this is really the kind of structure which I would like to present during my lectures. Quantum non-locality is central from, first of all, one point of view. If you start from very elementary quantum mechanics, superposition principle, linear kinematics, or linear Hilbert spaces, and things like that, you have then the tensor product. From that you can introduce the measurement problem. But this is kind of dead end, because you can't really measure anything here. Although it's a measurement problem, there isn't really something that you can measure and bring down the problem to some numbers that you measure, which is large, small, or whatever. Another consequence of the tensor product is that you have entanglement of distant systems, and this is my definition of quantum non-locality. So you have these, and here now you have something that you can test. You have the famous Bell inequality. When you can do experiments, of course experiments have loopholes, but at least you can do something here. So this is really very central. Now it is central also in the sense that it has connections, very nice connections, with two other very important fields of our science, relativity and information theory. Here information theory really means that the Shannon information theory. And I think one can really argue that relativity, quantum mechanics, and Shannon information theory are the three major conceptual breakthrough of this century, at least of the first half of the century. And this breakthrough happened independently, quite independently, you may say. And they also use different concepts. For instance, here it's deterministic. Here we have this famous quantum probability. We add amplitudes. Here it's classical probability. And nevertheless, these boxes or these concepts have close interactions. This one is known for a long time, and I'm going mainly to insist that actually combining these you get out very nice consequences. So this now appears as a consequence of quantum non-locality. So again, quantum non-locality is central herein. And on the other side, this more recent discovery that there is a link, a very productive connection between information theory and quantum mechanics, specifically the tensor product or the entanglement aspect of quantum mechanics, leads to all this quantum information processing. I will mainly emphasize this application, quantum cryptography, and show that there is a very explicit and direct link between violation of Bell inequality, which was historically motivated by local hidden variable, nothing to do with information theory or security of the internet or whatever, and quantum cryptography. So nowadays one can, for instance, present all these Bell inequality or entanglement stuff without any reference to local hidden variable. And I think that makes all the field again interesting. I mean, it has always been interesting, but there's a new viewpoint which puts new light onto the problem, and which I hope you will enjoy. So the idea is that today I mainly go through these red lines, so ending with a little bit of philosophy, but only very vaguely. It's not the main issue. But so the red line is for today, red connections for today. Tomorrow will be essentially the green ones. So the connections to this information, quantum information processing. And then on Thursday, it will be Hugo Zbinden who will talk, and he will talk essentially about experiments on Bell inequality, experiments to demonstrate quantum cryptography. You will see that they are quite related, or not only conceptually as it's drawn here, but also the technologies involved are related, and so he will talk about that on Thursday. And on Friday, I will come back and mention the blue line, the blue connections here. So I'll put that maybe on the side and possibly come back to that from time to time. So let's start with the elementary introduction to quantum non-locality. Elementary not in the sense that it is conceptually simple, but I don't want to do any mathematics, so mathematically it's extremely elementary. So first we start with the superposition principle, and here it just means that if you have mathematical objects which represent physical states, then this principle tells you that you can add these objects, and this addition, the result of this is again a mathematical object, which again represents a physical state. And so this is very powerful, and of course if you add a little bit of techniques to that, you get the Hilbert space. Now, as it stands here, it's very difficult to test, because it doesn't really tell you how to produce physically these states. So it's more really a kind of mathematical assumption. Now, if you apply this superposition principle to composed systems, or systems that are composed of subsystems, and we have them, of course, in classical physics, we have them in quantum physics. Every physical theory has, of course, composed systems. So here I call them A and B. So here is, for instance, a representation of a possible state of this composed system. The first system, the A system, is in state represented by phi A, and the second one by phi B. Same with psi A and psi B. So for time being, this is just a kind of notation saying that I describe them on the same piece of paper. But now, applying straightforwardly the superposition principle to that, I can add them, and the result of that should again be a possible state. And these are the so-called entangled states. And these, I will argue for a while, this entanglement and this fact that you can add product states, these kind of states are called product states, is really the most central feature of quantum mechanics, which makes it non-classical. I know that Feynman claimed that the most essential feature is the two-slit experiment, which is of course also related to the superposition principle, but two-slit experiment is a single particle, applies to single particles, and I'm going to argue that this one is even more profound and more leads to more results. Now think first for a short while these kind of states, where one of the states, the A state for instance, is something that you would like to call a measurement apparatus. Then this is at the basis of this famous measurement problem, which I promised I'm not going to talk about, so I leave it aside. You can also just think A is a cat, and then you get Schrödinger cats. Again, this is nice conceptually, but you can't really do anything with that because you cannot do it in the lab. You cannot go and measure something with this. So let's leave it aside, but it is interesting. Maybe just one thing I would like to say here, this measurement apparatus does not need to be so large. It does not really need to be macroscopic. Usually you read macroscopic. For instance, it could be just on a photographic plate. You have a photon hitting that plate, and you have some silver atoms that register the photon position. And you can then develop that photographic plate a year later. So the amplification process can be really delayed much in the future. And I guess we all agree that the photon is recorded at the time the picture is taken, not a year later. So it is not so simple here, but still it's not precise enough, sharp enough that I can now go and say, let's make an experiment, and that will be a conclusive experiment. Now there is another possibility to look at these entangled states. And this is when the two systems are spatially separated. One is there, the other one is there. They are very well separated. You can very clearly distinguish one is on one side, the other one is on another side. And then these states again have non-classical features, and this is now really quantum non-locality. So I like really to introduce quantum non-locality just as entanglement between spatially separated systems. And this is really an essential feature of quantum mechanics, And this one, we shall see, can be tested, and thus is of quite great interest. So I argued that this tensor product and non-separable states are the essential feature of quantum mechanics. Can one see that? Yes. Here you have a two-slit experiment. It's a waterfall. I'm not really sure one can see that very clearly, but so you have water falling down this way of the rock and water falling down the other way. So this is a two-slit experiment. And you can have a cork floating on the water. The cork very clearly will pass only one way or the other way. Nevertheless, the way the cork will behave here down depends on whether both slits are open, as in the picture, or if you close one slit, it will have an effect on the trajectories of the cork afterwards. And so the two-slit experiment has actually a classical picture, and this classical picture, if you formalize it better, is actually Bohm's model of quantum mechanics. So that is the reason, because of this existence of the Bohm model, that I think that just a two-slit experiment is not the main feature. Apply the superposition principle not to one particle, but to two or more than two. And then you get really something which has no classical counterpart. You really enter really in the quantum world. And we'll see also for the application of quantum information processing that this is really important. So here we start with one of these entangled states, for instance of a green photon and a red photon. And so the state is as it is written here, so it means that there are a superposition, there's a superposition of two possible states. Either the green photon is in this state psi1, and then the red photon is in the corresponding state phi1, or the same with the other indices. And now we think of this possibility that we can separate in space the two photons. So one is going to the left, the other one to the right-hand side. Now if you stay only on one side and forget about the other, what we see here on this side is just a mixture. It's a mixture. Half of the time we get a state phi1, half of the time we get a state phi2. So if these are polarization states or four-gram polarization states, for instance, this would correspond to completely depolarized light. And as a consequence, if we put an analyzer here, in general it could be any measurement instrument or could be a polarizer, with some settings, some knobs you can turn around, and when you detect the particle, and you can count this number of particles so that the single counts, a function of the settings, you get essentially a constant. Well, in principle, it's exactly a constant. If you do a real experiment, of course, you have some noise. And the same on the other side. But now, because it is really such a state, and because you have two particles, you can, after recording all these data, you can compare them, go to compute coincidence counts, and the coincidence counts, because they are produced this is not a mixture of either this part or that part, it is this and that, so the coincidences are really produced by both of them. And when we add wave functions, probability amplitudes, then we get interferences, and indeed in the coincidence counts you can get these nice two photon interferences or two particles interferences. And these you can measure in principle. And so now here we have some prediction of quantum mechanics that can be measured in the lab and even outside the lab, as we shall see. Okay, let's, before even coming to Bell inequality and this kind of stuff, go a little bit more just into the consequences of the existence of entangled states. This is what I call state preparation at a distance. And very clearly, at the time of Einstein, Bohr, and Schrödinger, they had no Bell inequality at the time. Nevertheless, they had a very clear intuition that this non-locality was something new. They had different interpretations about its meaning, but very clearly it was something new. Everybody at the time already, at least the best physicists, knew that there was something really new. So before introducing the Bell inequality, I'd like to go more into the consequences of the existence of these entangled non-local states. So how can you prepare a state at a distance? You start with an entangled state of a combined system, So it's the A system combined with the B system, or A subsystem with the B subsystem, which together produce one AB system. And now on one of them, let's say the second one here, you measure something, and B is the operator which represents a certain physical quantity which belongs to this second subsystem, the B system. Now you can write this operator in this form, so one-dimensional projector with eigenvalues, and psi then can always be decomposed using the basis of the eigenvectors of this operator. So it can be written in this form. Now, very elementary, again, quantum mechanics. You measure B, the result is an eigenvalue, let's say lambda j, and that happens with a certain probability, which is the square of the norm of Cj. Now, the consequence of that is that once you have this result, that the B observer has this result, he can make all the predictions for the A system, and all the predictions he can make are all compatible with the assumption that the A system is in this corresponding state alpha j. Now, if everything is as if the system would be in that state alpha j, what difference does it make to say that it is in this state? There is no difference, empirical difference. It is as if it is in that state, so let's say it is in that state. So now we have that the distant system is no longer in the original state psi, it is now in a different state, alpha j. But of course the distant observer, he doesn't know the results here, so he has a classical mixture of these states with classical probabilities, and the weights or the probabilities are these square norm. So for the distant system, the distant observer, his state, the row after the measurement of B, is of that form. It's really just a classical mixture of pure states with some weights. So this is preparation at a distance. And this is, first glance you may say, surprising, it's impossible, how can I from here prepare something there? It would be even a contradiction with relativity if I could really use that and exploit this preparation at a distance. However, if instead of measuring B, the B observer would measure some different physical quantity, B prime, something different, B prime, then this decomposition would be different with beta primes and alpha primes and C primes. So here at the end we would get C primes and alpha primes. Now, very elementary mathematics, I don't want to do it here, but it's really quite straightforward. You would get different C's, different alphas, but the sum is the same. So the density matrix here at the end, the mixed state, is the same. And because you always prepare the same state, the same quantum state at a distance, you cannot use this quantum non-locality to signal. So no signaling, this is really very important. And because of course, if one could signal, there would be just a huge conflict between quantum mechanics and relativity. Now the fact that one cannot signal means also that there is no conflict. So we have some kind of non-locality, maybe we can even say the word is not well chosen, but this is certainly a kind of non-locality which is compatible with relativity. Really should be emphasized. Okay, and now because of that you can also now define reduced states. Okay, I'm just coming to the Bell inequality, but I already introduced the word because of course all of you have already heard of it. One important thing is that entanglement is not something which is very rare. Entanglement is not the exception. Entanglement is the rule. Actually, if all entangled states, an entangled state is anything which is not a product state. So entangled states happen with probability 1, or if you like, the set of product states is a set of measure 0. Moreover, all pure states do violate some Bell inequality. So violation of Bell inequality, so the possibility to experimentally demonstrate that these states are indeed entangled, is not something that you can do only for some very specific states like the singlet states you heard about. It's valid for all pure states. So it's really generic. It's really something very important in this sense. Now it's also interesting that although entanglement is very central to all this issue, there are still a lot of open questions. although people work on that and the literature is so huge, there are still some even very basic questions which are open, and I'd like to mention some of them. For instance, if instead of looking at pure states, you go for mixed states. For mixed states, we still don't know any constructive criteria just to decide whether a state is entangled or not. I give you a density matrix and ask you, is it entangled or not? In the sense, can I write this state as a mixture of product states? And for most of the examples I could just draw, you could not find the answer. And that is, I think, quite surprising that one doesn't know how to classify these states for a mixed case. Actually, one knows how to do it if both subsystems are spin 1/2. But as soon as they are more complicated, one doesn't know the answer yet. Okay, so let's come to Bell inequality. And I'll present it first like that. So in order to test Bell inequality, you need somewhere a source. Let's put it here, for instance. A source is something which will produce a system composed of two subsystems. And you need somewhere a source because whenever you get the subsystems, you must know which subsystem goes with which other one. So you need to put some tag on it. Usually it's the timing. And actually the two subsystems don't need to be produced together. They could even be produced independently, but somehow they have to have in their common past something which puts a mark on them saying they belong to the same state. But in practice we have just one source here. Hugo will say much more about that day after tomorrow. And then one of these subsystems, you send it to some location, and the other one to some other location. So in practice, of course, here we used optical fibers. But in principle, that doesn't matter. So you just really separate them. And if you can separate them by a large distance, it just makes it more dramatic. But for the conceptual point of view, all what is needed is that you separate them, one end of the lab and the other end of the lab. Now there is a physicist here, and he can make some measurements. Same, of course, on the other side. And so the measurements, to take a simplest case, we need a measurement that has at least two outcomes. Of course, must be at least two. So we shall take measurements that have two outcomes, two possible outcomes. And also we shall assume that this physicist has a choice between two kinds of measurements. One, which I will call A simply, the A measurement, and the other one is the A prime measurement. And on this side, we shall call them the B measurement and the B prime measurement. Now, actually I'm using the same letter for the measurement and the measurement outcome. So the result here, there are two possibilities, and I decide for convenience to label them +1 and -1. That's just convenient. So these are the possible outcome in case the first physicist measures A, he gets either +1 or -1. Same if he measures A prime, and the same for the B and B prime on the other side. Now, I just decide, because this is a long history, so I can just take advantage of all that, and decide to look at this combination. So I get a result A, I get a result B, so I can multiply them. Of course, the result will again be either +1 or -1, and then I can add that with A prime B, minus A prime B prime. And trivial algebra, I get this result here. And now there are only two possibilities. Either B is equal to B prime, and in this case the second term cancels, and the first term is clearly bounded by 2. Or, alternatively, B is equal to minus B prime. In this case it's this term which cancels, and the other one which is bounded by 2. So we get these elementary results that this combination is smaller or equal to 2. Now, the argument continues. If A and B are well separated, well distant, and nowadays we would even say the separation is space-like, but notice that space-like is not a concept of quantum mechanics, it's part of relativity. But so if the system are well separated, even not space-like, but very well separated, then it is quite natural to argue or to assume that the results on one side are independent of what I'm going to measure on the other side. So the fact that, for instance, the A physicist found the results +1, it's very natural to assume that this is completely independent of whatever the other guy at the other end has done, whether he decided to measure B or whether he decided to measure B prime or even whether he decided to measure nothing or to whatever. How could it depend on that? He is so far away. So it's essentially this independence. The result on A may depend on a lot of things, coming back to lambda, but it should not depend on what is going to be measured on the other end of the line, on the B. Lambda, this is now often called the local hidden variable, and this is the locality condition that we have this independence. So lambda, the fact that it is hidden is not so important. The fact that it's local is the important point. Lambda can be everything that describes the state of the A system, including the possibility including the state vector. So in lambda you can clearly include also the state vector, the psi, capital psi of the combined system, because the capital psi is decided when the two subsystems are still together, and when each of them fly apart and can take with them all the information that is there, including the information of what is the combined state of the two subsystems. In lambda you can have the temperature, if you really like, or whatever you like, including all possibly unknown, yet unknown parameters, whether they are unknown just because we don't know them now or whether they are unknown for more deeper reasons is not really relevant. Really the only assumption about lambda is that this has to be an element of a measurable set so that we can compute mean values or expectation values. This is necessary. But that's the only real assumption on lambda. So it's very, very general. So having this independence, we get that the product, the value of the product AB for a given lambda is just the product of these. And here we have no B dependence, and here we have no A dependence. Of course, the same as this holds for the B also. And because we have that lambda has some probability distribution and is part of a measurable space, we can define the expectation values in the very natural way. I know an integral or an expectation is a linear operation, so we can just take expectation of this inequality and we get this inequality here. Now it's just the same with the expectations here now. And this is one form of the Bell inequality. It's actually the form which is due to Closer, Horn, Shimony, Holt, which is the most useful form of the Bell inequality, although you have many other forms. So really mathematically derived the Bell inequality is very trivial. To formulate the assumption is not very difficult, but actually conceptually it's quite delicate, and even with experience you still get in trouble sometimes. So again, the logic of the Bell inequality is really from the locality assumption, you conclude this independence. The result on one side is independent of what is measured on the other side. And this is physics. And then once you have the independence, which is formulated as a mathematical relation, you do, well, mathematics or algebra, trivial things, and you get the Bell inequality. So this is important, this logic, and I see quite often confusions here. People saying, oh, but the Bell inequality can be derived from the independence condition quite independently of the locality, so Bell inequality does not depend on locality. Formally this is correct, but the interest for the Bell inequality, why is it interesting? It is because it comes from a very plausible physical assumption. Here. Just some comments here. Here we've chosen the simplest case where we have only two measurements and two subsystems. But you can generalize that, and there's a large literature on that. For instance, you can generalize that to systems composed not of two, but of many subsystems. The reference I give here is just a recent one, which of course I know well. And in this one, you'll find the references to the older ones. This is by far not the first generalization to many subsystems, but you find the reference in it. And how can you do that generalization if you have a third possible measurement, C and C prime, done now on the third subsystem? Then you can just take the S2. The S2 is just the S I mentioned before. So this is S2. you take S2, you multiply by C plus C prime, plus S2 prime. S2 prime is the same expression where you interchange the prime and unprimed. Multiply by C minus C prime, and again the same argument, either C is equal to C prime, this cancels, or C is equal to minus C prime, this one cancels, so all that is smaller than 4. So it's a very natural generalization you can go on. And the interesting point here is that the violation, I didn't even say it yet, but of course Bell inequality is violated by quantum mechanics, come back to that. But this optimal violation of the Bell inequality, if you have many subsystems, so if you have a much more complicated composed system, this violation explodes exponentially. It goes like 2 to the power n minus 1 divided by 2. So it becomes more and more violent, this violation. Experimentally, what has been done so far, the best, is only n equal 2, which is very, very small, n equal 2. And it would be certainly interesting to go to higher dimensions here, and there is really good hope that in the next years, the case n equal 3, 4, 5 probably will be considered, and so that we get violation of Bell inequality by factor which should grow here. You can also, I'm not going to go into details, but you can also go to more than 2 settings on each side. Okay, so without quantum mechanics, Bell inequality would be a triviality, but the interest is, of course, that you have states, for instance, the singlet state, or actually any pure state will violate Bell inequality, and for that one, for instance, the singlet state, the form of the correlation according to quantum mechanics is minus the cosine of the angle between the 2 directions. Now here I have directions which are on the Poincaré sphere, or Bloch sphere, for people from solid state physics, and for these settings you get really the maximal violation, which is by square root of 2, so more than 40%. So it's a significant violation, large enough that you can measure it. I would like to advise this little paper, which is already old, but still very nice. I propose to put it in the copies of the transparencies that you should receive if you ask for. This paper, for instance, has one nice feature, is that you can give it to read even to your non-physicist friends, even to the people who are allergic to mathematics, and unfortunately I know that there are plenty, maybe not here, I hope not here, but around outside there are so many, and these people can read that. And it is understandable and fascinating. Good. So, we saw that quantum theory, didn't see that quantum mechanics yet in the lab, but quantum theory at least is non-local. Non-local in the sense that you have these non-local states, that you can do non-local preparation, or preparation at a distance, that you violate Bell inequality, and so on. And here, when people disagree whether this is an important topic or not, so I guess for you it's important enough at least that you spend an hour listening to me, but why is it important? I believe, of course, it's important. So I like to argue that there are really 2 good reasons for taking that seriously and to spend even more than an hour on that. Okay, a little bit schematically, I called one physics and the other one money. You could also say this is basic physics, this is applied physics, or some people may say this is the physics and this is philosophy, whatever. There are 32 different kinds of motivations here. From what I call here physics, is that if you really test this quantum non-locality, you find out that indeed the experiment agrees with the theory, then let's take this theory really seriously. And according to the theory, we have entanglement forever. It lasts forever over any distance, any number of particles, any masses. It's there forever. So the only logical consequence that I see, consequence, I mean worldview, which is compatible with this fact, entanglement forever, is one form or another of the many worlds, the Everett's many world interpretation. I'm not going to go into that, but really many people, I mean, take that very seriously, many universes. I don't even exactly understand what it means. For me, it is very strange, but David Deutsch finds that very natural. He calls that the multiverse. He has a book called The Fabric of Reality, that you can read, where he really takes the idea extremely seriously and extremely far, so far that at the end I find it completely absurd, but I mean, he takes it seriously. So, and there's quite some consistency in it. It's not that they are just brute mistakes in it. Everything is entangled, so it has huge consequences for our worldview. And this is certainly historically all the motivation, going even back to Einstein and probably also Bell, and many people have their motivations here, including myself. But here we essentially see paradoxes. We can fight about the ideas, whether many worlds make sense or make no sense, and what? Well, here we have something more. Here we have something very interesting happening, and quite recently happening. All these paradoxical aspects of quantum mechanics have now been realized to have a positive counterpart. They can be used for something. And they can even be used for something which is useful enough, or potentially useful enough, that really even the people who are doing the science management get excited. It has to do with security, with cryptography. I'm coming back to that tomorrow more in details, but it's really becoming interesting. You can do what people call quantum computers. And for instance, with a quantum computer, you could break the security systems because you could factor large numbers in an efficient way. So it has dramatic consequences. And the fact that now we look at entanglements no longer just as a source for paradoxes, but as a resource to be productive, changes the picture completely. And this is really a very significant motivation for all these fields to regain momentum presently. And indeed, tomorrow I'll show you that Bell inequality can be really presented without any reference to local hidden variable, just by saying, I want a secure communication system, which is a much more practical, of course, viewpoint than local hidden variables. Moreover, there is really money here. The European Commission is most likely going to launch a dedicated call for quantum information processing. Major national agencies also have money for that. The same in the States, the same in Japan. So all that is based on the assumption that there is entanglement, maybe not forever, but at least enough that we can really make use of it. To make use of it, we need entanglement for thousands of qubits. The best experiment today is between 2 and 3. I mean, 3 has been done, you can still argue 2 is clear. But from 2 or 3 up to thousands is a big step. And I know some cosmologists apply it to the universe, but here, let's make it practical. We would like to make or to test whether it is really possible to make a quantum computer which will really be more efficient than a classical computer. So it makes the problem very concrete and practical. And so indeed, one of the first questions is now, is a quantum computer really faster than a classical computer? I told you before that with a quantum computer, one could factorize large number in an efficient way, which is something one cannot do today with a classical computer. But the situation is the following. One cannot do it today with a classical computer because either it is really impossible or because we don't know how to do it. There is no proof that it is impossible to do with a classical computer, but it's clear that nobody has found it, or at least if somebody has found it, he didn't publish it. But let's suppose he did, nobody has found it. So the question is open. Is it really much faster, a quantum computer? And I think it's a good question here, because whatever the answer is, it's a productive answer. If the answer is yes, then, of course, if you can do something which is better than a classical computer, knowing that classical computers, well, it's quite often a mess, but it's also quite useful, and so you can argue, let's invest in the field, let's make progress in that. As well in the technology, as just conceptually also, what does it mean that a quantum computer can do more than a classical computer? It means that actually questions like the possibility to factorize large numbers, or these kind of questions which apparently are purely mathematical questions and belong to mathematics, now belong to physics, because it depends on the nature of the physics. If physics is quantum, then the answer would be yes. If physics is classical, the answer would be no. So the answer to a apparently mathematically looking question would become physics. And if you go back to David Deutsch's book, he at the end concludes that actually physics is the basic science. It comes even before mathematics. I don't want to go into that direction, but clearly the mathematicians do not agree and want to prove the opposite. So it's a lively and exciting debate. That's in the case, the answer here is yes. So quantum computers are really more efficient. And if the answer is no, there are also very interesting consequences. If indeed a quantum computer is not more efficient, it means that classical computers can do the same. Consequently, classical computers can factorize large number efficiently. So if you can break a security system with a quantum computer and classical computers are as efficient, then you can also break the security system with a classical computer. Simply, you don't know how to do it yet, but it means somebody could find that tomorrow. And that would be just a mathematical finding, finding the good algorithm, and it would have such a dramatic effect that it's easy then to go to the funding agencies and tell them that something should be done. So whatever the answer, it is a positive answer. So I have just one transparency on interpretations a little bit about this, the physics part. So that was on the money part, now on the physics part. Quantum non-locality implies that entanglement is robust, is there forever, assuming it really extends to distances and all that. So we have everything is entangled, in theory. However, why is it that we don't see that? Why is it that we don't notice it immediately that we are all entangled and everything is entangled here? And here the key word is decoherence. I'm not going to go into details what decoherence means, but essentially it means that all the phase relations between all these different product states becomes so complicated that you lose track of it. So essentially decoherence means it becomes so messy that you can no longer follow it. And I don't like this answer at all, although it's the official answer. Official in the sense that this follows from quantum mechanics very naturally. I don't like it, and I like to put in opposition actually Karl Popper's epistemology, where he defines a theory as scientific if and only if it can be tested or, according to his words, falsified. Now what is that? A theory which tells you everything is entangled, but don't worry, you cannot test it. Is that a scientific statement or not? It's a question I'm raising. And so if really quantum mechanics prediction of entanglement forever cannot be tested, shouldn't we prefer some alternative theory? According to Karl Popper, if Karl Popper's epistemology would really reflect exactly the way physicists behave, then we would immediately give up quantum mechanics, I believe. But of course, the physicists decide how we behave, it's not Karl Popper. So we keep quantum mechanics, including myself, because it's very efficient. And the reason that we keep quantum mechanics is not because there are no alternative theories. There are alternatives. There is Bohm model, which I have already introduced, which is extremely nice as long as you have a single particle. But of course, a universe with a single particle is boring. And as soon as you have many particles, Bohm's theory also becomes non-local and also has its own problems. You have the model of spontaneous localization, spontaneous continuous localization by Girardi, Rimini, Weber, and Pearl. You have quantum state diffusion. So you have some alternatives. However, admittedly, none of these alternatives is as elegant as quantum mechanics. None has all this nice symmetry. None of them is as productive if you want to go to quantum field theory or if you want to go, let's say, outside the real core of quantum mechanics. And so I think it's really for that reason that quantum theory is still the accepted theory. But the fact that one of these most dramatic consequences is in principle non-testable makes it, well, disgustable. Okay. So let's continue about alternatives. So actually, the experiment will be presented the day after tomorrow, but I think I can already tell you that the experiment confirms the theory, and that in this sense we can really continue on the assumption that entanglement exists, at least for two particles, for two photons, and so on. So given also the experimental evidence, what alternatives is there? Is there still an alternative? And yes, there are some. There are some, first of all, because we are going to do real experiments. We have done, and other people have done, real experiments. In real experiments, you have things which are not perfect. So you get into loopholes. And one very important loophole is this detection loophole. And I would like to spend some time on that loophole, which is explained on this transparency. So the basic idea of that loophole is that whenever you do a measurement, you have this measurement instrument, you have your quantum system to be measured coming into that, and in principle, you have outcomes, number 1 and number 2. For us, it's even enough, 1 and 2. But in practice, what happens very often is that your detector or something fails and you get no result. All the experiments here have been done with photons. And so you have lenses, so you have optical fibers, so you have something, and you have losses. So sometimes the photon gets lost, absorbed, or the detector is not efficient. In practice, our detectors, you'll learn about that tomorrow, the day after tomorrow, are not very efficient. So this no result happens quite often. Now, if there is a local hidden variable somewhere, or something unknown, an unknown variable, it is very, very plausible that this unknown variable actually has an effect on the losses and on the detection efficiencies. For instance, if we would not know about polarization, let's say we don't know about the polarization of photons, we would know only about the frequencies, then this would not, nevertheless, even if we would not know polarization, detectors are sensitive to polarization. And it's not enough to ignore polarization to make the detector non-sensitive to that. So it is possible that the probability to get no result actually depends on the local hidden variable. It's a very natural assumption, actually. And if you make this assumption that depending on the hidden variable, I'm going to be very explicit here, you get no results with a different, the probability of getting no result depends on the local hidden variable. And in this case, you can violate Bell inequality even with local hidden variables. It goes as follows. Let's suppose that we have again our A and A prime, B and B prime, and the results can be only plus and minuses. So here I have 8 possible values for the hidden variable. So the probability space has only 8 elements in this simple model. Let's mainly concentrate on that line. So let's suppose the hidden variable, local hidden variable, takes the value lambda 4. Then that programs the first particle, in case it is measured with the setting A, to answer plus 1. If it is measured with the setting A prime, it gives the result minus 1. And for the other particle, the B particle, if it's B that is measured, it's again minus, and B prime is plus. As a consequence, if the local hidden variable value is lambda 4, the product A times B, so it's A times B, is minus 1. A prime times B minus minus will be plus 1. And so on. Very elementary algebra. You do that, you fill these columns, so for the 4 possible combinations, then you can compute the mean values. So here it's all, you have 6 times plus, 2 times minus, trivial, you get as a mean 1/2, and then the S parameter here will take the value 2. So Bell inequality is not violated, and it cannot be because the result of the A measurement depends on lambda, but does not depend on B or on B prime. So it's a local hidden variable, and it can't be larger than 2 here. But now let's suppose that for this value lambda 4, the second particle is programmed such that whenever the question is, or the measurement is B, the particle disappears. It does not get detected. There is a detection which depends, the detection efficiency depends on this hidden variable. Here it depends extremely strongly, since the particle not even has a lower probability to be detected, it just disappears completely. In that case, for this value of the local hidden variable, you never have AB, because B is never get an answer, so he gets here the empty set, let's say. The same for A prime B. However, you get results in the two other cases. Notice that here, so all the results in parentheses are the ones that disappears. So you have 2 that disappears out of 8. So it means that you have an efficiency of your detector, the efficiency that you can measure if you do that would be of 75%. In practice, most detectors, optical detectors, have even much lower efficiencies. Now you do again you compute the mean values here. So here you get only plus. All the other ones, the ones that were minus before, now no longer appear. So you get the maximum value here, and the S parameter, the Bell parameter, becomes 4, which is much larger than 2. It's even larger than allowed by quantum mechanics. So it's a very simple model. It doesn't really take time to find that out. That you can violate Bell inequality with a local hidden variable. The hidden variable is still local. Even whether this particle here will be detected or not does not depend on what is measured on the other side. And you violate Bell inequality. So the detection loophole is, in my opinion, a serious loophole. The reason why it's not taken more seriously by people is that it is quite artificial, I have to say. I mean, these models are presented here, or even more elaborated models. They are always ad hoc. You have to make them for the experiment. But it's not so difficult to make. So from a logical point of view, there is still here something that should be improved. Or maybe, what did I have in mind then? Okay, I think I'm going to stop here and say more about the other ones tomorrow, so that we have some time for some questions, since nobody interrupted me so far. Thank you. Yes.
Could you specify precisely how far systems have to be separated in order to be fault separated? Can you repeat the question?
The question is, how far have the systems to be separated to be called separated? No, I cannot. I mean, separated, actually we use the word in 2 different meanings. From the logical point of view, 2 systems are separated if they can be described with product states. So this is just a mathematical definition. Now, intuitively, when we say separated, or more specifically, I should always say spatially separate, so at a distance. This is, I mean, of course, as soon as the distance is larger than the coherence of the object, I would say they are separated. But it's a continuous it goes from 0 and then it goes continuously. So there is no so clear and sharp definition. Now, it's not because there are no sharp definition that the concept is meaningless. If you have systems which are really kilometers apart and the registration time is much shorter than the time it would take for information going by the speed of light from one end to the other, then they are clearly separated. So when they have maybe 1 micron, I don't know whether 1 micron is good enough, but 10 kilometers is good enough. Meters would be good enough also, of course.
I'm asking because we have in particle physics the decay of a spin 0 particle into spin
the count
1 particle since 30 years, and people say, oh, that's not a good test because they're not separated when their spins are...
No, but I would also, I think all the idea, of course, historically and all the connection with the relativity side, yes, I forgot to put that from time to time again. This connection here, spatial separation, is important because it's important for relativity. But internally in quantum mechanics, spatial separation is not important. And for quantum information processing, for the quantum cryptography, it may be important, but for many other applications, it's not so important that things are separated. You don't want your quantum computer to extend over space. You just want it to work, to operate. So what is important is entanglement. This is really part of quantum mechanics. This is the resource which is useful here. So I would say that if you have a way to make experiment that tests entanglement in new ways, it is a good experiment. Whether it is connected to relativity or not, it nevertheless is interesting, because entanglement is the key.
Could you explain why
Yes, I can, but not in 1 minute. So the question is, why is the quantum computer more efficient? So first of all, we don't know whether it is more efficient. So this is one thing. But why is it? Do we believe it is more efficient? Essentially, the intuition is that in a quantum computer, you do all the information processing while keeping the coherence, the quantum coherence. So instead of just having one input, which is transferred to one output, you have a superposition of many inputs. They are all processed coherently, and so you get, as an output, the superposition of all the possible outputs. Now, if you're just interested in one of the outputs, it's not good. But very often you're interested in some kind of global feature of many, of all the possible outputs. For instance, if you want to know whether a function is a constant or not. Classically, you would have to compute that function very, very often, and you always find the same result. At the end, you get confident that it is a constant. Of course, as soon as you find two different results, you know it's not a constant. But there, clearly, for this kind of question, you're not interested in a value, you are interested in a property of many values. So if you can compute all the values in parallel by quantum parallelism, by coherently processing all the possible inputs, and then be able to check that at the output all the values in superposition are, for instance, all the same, then at once you get the answer whether this function computes a constant or whether it's a more interesting function. This is the general idea, but I mean, it would be a full week lecture on quantum computer just to start really giving more detailed explanation of that. And moreover, it's a field which is extremely active, so things are evolving extremely fast. You can also ask about entanglement. Entanglement, I defined it here in a very simple way, only saying it's the opposition of product state. Everything which is not a product is entangled. That's good, that's a good definition. But as a resource, we would like to measure entanglement and to say how much is it entangled? Is it more entangled, less entangled? Can we swap entanglement, go from one way? Can we concentrate entanglement? And there's a lot of work going on that. I'm going to present a little bit on that also tomorrow. But it's really these kind of questions which are ongoing, and it's quite surprising, and I think a nice surprise to see that so little is known, because it means that there is still so much to be found, even in relatively elementary quantum mechanics.
One has checked the Hanbury, Brown and Twiss effect. Do you know that? That's it.
Where has that been checked?
Hanbury, Brown and Twiss.
Yes, yes.
That's entanglement. You have the classical thing is you have a faraway star which sends photon from two places, and you have two detectors which detect them simultaneously, coincident. And now the light can go one way or cross.
Mm-hmm.
And the probability amplitude that has to be added, and then you find variation in the probability of the coincidence if you detect.
Yeah. What is the visibility? I guess the visibility is not as large to violate Bell inequality.
It has been in the astronomy. It has been used to measure the size of the star or another star, and here at CERN, it has been used for the size of the source of particles when you shoot, for instance, lead on lead.
Okay, so it's one more evidence that entanglement holds.
The business here.
Okay, very good. Thank you.
Okay, so before we take the rest of everyone has time, just a reminder, please speak up copy here for this course, that you need to get copies of the transparencies and where you can put your comments on the lecture. Thank you very much again.